Okay, we will start the defense of the student Catarina Aydar, a master dissertation at the IAG. I would like to first thank all the people that are the three people that are participating in the defense committee. They are Dr. Maria Monserrat Vilar Martin from CSIC INTA Spain, Professor Dr. Lee Luiz Dor Jr. from Univap, and Dr. Walter Junqueira Maciel from the IAG. We will proceed then for the student to give a presentation of the thesis for a maximum of 1 hour, and then the evaluators will be able to ask the questions and evaluate the student. Thank you all. You can start, Catarina.
Thank you, Claudia. Just a second that I will share my screen and then I start. Okay, do you all see my screen and my cursor?
Yes.
Yes.
Okay. Yes. Thank you. So I'm going to start now. Good morning or good afternoon, depending on where you are. My name is Catarina Aydar, and I'm going to present you the work Diagnostic Diagrams for the Classification of Galactic Nuclei, Comparison of Traditional and Alternative Diagrams. Before we start, I would like to thank the committee for being available to help me to improve my work, and also to thank my advisors, João Steiner, Cláudia Mendes de Oliveira, and Roderick Overzier, my institution, Instituto de Astronomia, Geofísica e Ciências Atmosféricas da Universidade de São Paulo, and the agencies that financially supported my master's degree, FAPESP and CAPES. The structure of this work is divided in 4 parts: the introduction, the sample, the analysis, and the conclusions and perspectives. In the introduction, we present the astronomical objects that we aim to classify, and some of the traditional tools that are used in the literature to distinguish them. Hence, we will introduce galactic nuclei, photoionized gaseous nebula, and the main drivers of such photoionization, that are active galactic nuclei, AGN, and stellar processes. We also introduce the main diagnostic diagrams that have been used in the literature to differentiate AGN and stellar ionization in galactic nuclei. Then, we present the sample that we have considered, which is a subsample of the Sloan Digital Sky Survey. In the analysis, first we discuss the traditional diagnostic diagrams, the different classification schemes proposed in the literature, the transition objects, and the issues of misclassification. Then, we present alternative diagnostic diagrams and the proposed classification schemes. And in the last part of this section, we will discuss the theoretical models that we have run with CLOUDY and Starburst99 codes, with a new proposal for the nitrogen abundance in star-forming regions. At last, we present the conclusions of this work and the perspectives for the next steps. The main goal of this work is to provide new tools to study galactic nuclei. We want to answer the question, what is ionizing the gas in the nuclei of galaxies? Is this high surface brightness associated to stars and star formation, or to the accretion of matter onto a supermassive black hole? In this work, we are focused on the central region of galaxies, which are the galactic nuclei. The nuclei of massive galaxies host a central supermassive black hole and can also be reached in stars and gas. The galactic nuclei we are going to study present emission lines in their spectra, with strong forbidden and hydrogen recombination lines. This indicates the presence of photoionized gas, and the source of the photoionization can be associated to activity from the supermassive black hole or hot stars, with both such mechanisms being able to produce shock waves, which in turn can enhance the intensity of the emission lines. It is also important to emphasize that these components usually coexist in the nuclear environment. Therefore, the classification schemes seek to identify which is the dominant power source acting on each galactic nuclei. The spectra of nuclei photonized by stars or an AGN have different features with regard to the shape and intensity of the emission lines and to the shape of the continuum. This is figure 1 from the annual review by Louise Ho, 2008. And we see the main spectral difference of some of the typical low luminosity active nuclei. So here on the top, we have a spectrum of a high ionization AGN, which is denominated Seyfert. Here in the middle, we have a liner, which is a low ionization AGN. And on the bottom, we have a star-forming region, which is denominated H2 region. Gaseous nebula photoionized either by an AGN or by hot stars are actually very similar, and the main differences are associated to the harder radiation field from an AGN. The degree of ionization at each point of the nebula is defined by the equilibrium between the photoionization and the recapture of thermal electrons by the ions. This is an example of a typical photoionized nebula, and it's characterized by a central ionizing source surrounded by this H2 region represented here in blue and red. In blue, we have a region of intermediate and high ionization species, and here in red, we have a partially ionized zone with the coexistence of neutral and low ionization elements. Sorry. Surrounding this H2 region, we have an H1 region, which is a neutral region, here shown in yellow. The main difference between the gaseous nebula photoionized by AGN or by hot stars is the size of this red region here, the partially ionized zone, which will be larger for AGN. Next, we will describe the main central ionizing sources that we are going to study, which are AGN and H2 region. Active galactic nuclei are the direct manifestations of a supermassive black hole that is accreting matter in the center of galaxies. They are not rare, but rather represent a natural episode in the life of galaxies, and their spectral energy distribution, SED, has both a thermal and non-thermal emission contribution, and it goes from radio to the X-rays. The most relevant intrinsic parameter that differentiates AGNs is the accretion rate. Here, we see the main scenarios for the accretion modes of AGNs as proposed by Hackman and Bass, 2014. Here on the left, we have the radiative mode AGN, where we have the central supermassive black hole surrounded by an accretion disk of the infalling material, a broad line region with clouds that have high velocities and high densities, and further from the black hole, we have the narrow line region, which are clouds with lower densities and lower velocities. And this is also surrounded by this dusty obscuring structure, which we believe to be more clumpy than what is represented in this simple scheme. These objects present Eddington radius above 1%, which indicates that they have an efficient conversion of the gravitational potential into radiation. Here on the right, we have the jet mode AGN, which is more typical of liners. Sorry, I didn't mention this is more typical for Seyfert galaxies. And on the jet mode AGN, we do not have an accretion disk, and we also do not have a broad line region, but we have this narrow line region, and we have this advection-dominated inner accretion flow, surrounded maybe by a truncated thin disk. These objects present Eddington ratios below 1%, which means that they are radiatively inefficient to do the conversion of the gravitational potential into radiative energy. And their main energetic output is via jets. Therefore, the two types of AGN we aim to classify and distinguish are intrinsically different, with Seyferts being associated to more efficient accretion and higher ionization, and liners with less efficient accretion and lower ionization. Also, Seyferts are usually found in gas-rich environments such as spiral galaxies, and they are associated to a phase of active growth of the central black hole, while liners are typically associated to early-type galaxies that are gas-poor, and these black holes tend to be more massive and passive in a later stage of their evolution. The acronym LINER stands for Low Ionization Nuclear Emission Line Region. However, in some galaxies, we might find extended emission further from the nuclei, and that is not directly associated to an AGN, though their spectra is similar to bona fide liners. Their photoionization source are mainly associated with shocks or hot old stars as post-AGBs, but it can also be due to diffuse ionized gas, cosmic ray heating, and X-ray binaries. Now, we will introduce the other possible stellar phenomena that can ionize gas, which are young ONB stars, Wolf-Rayet stars, and old post-AGB stars that will emit ultraviolet radiation. Newly born stars are able to ionize the gaseous nebula from which they are formed. The ONB stars are the most energetic stellar classes, and they are very massive and hot, and therefore they have a short lifetime in the main sequence. If the star formation in a galaxy is very intense for a certain period of time, this galaxy will be denominated starburst. The H2 regions and star-forming regions tend to form a sequence with varying metallicity, which is called the star formation main sequence. Wolf-Rayet stars are the latest stages of evolution of massive stars. They present high mass loss rates such that their cores get exposed. Hence, they present high temperatures and hard radiation fields that are capable of ionizing the surrounding medium. These objects are more frequently found in high metallicity environments. Another stellar population that is capable of photoionizing the interstellar medium is the one of hot, low-mass evolved stars, HOMES. These post-asymptotic giant branch stars are the phase between the planetary nebula and the cooling to a white dwarf. They are typically found in early-type galaxies or retired galaxies, and they can provide a spectra that is similar to liners. Now, the last topic of the introduction is about the diagnostic diagrams for galactic nuclei spectral classification. Their calibration can be empirical, theoretical, or can consider both approaches. We will focus on the diagrams that consider emission line ratios, and we can obtain information regarding the chemical composition, the ionization parameter, the density, the pressure, and the radiation field of the objects. From now on, we will refer to these lines shown here without explicitly mentioning their wavelengths. So we will talk about oxygen 3, nitrogen 2, sulfur 2 doublet, and oxygen 1, and also the Balmer lines of H alpha and H beta. The three diagnostic diagrams that were traditionally considered in the literature for the classification of galactic nuclei according to their dominant ionization and excitation source was proposed by Baldwin, Phillips, and Terlovich, 1981, and Veilleux and Osterbrock, 1987. The main idea behind the three traditional diagnostic diagrams is that there is an upper limit for the intensity of the emission line ratios for star-forming nuclei, distinguishing them from AGN that can reach higher values. In that sense, the two types of objects will be positioned in different loci of the diagrams, with the star formation branch to the left and the AGN branch to the right. The AGNs are associated to harder ionizing spectra, and hence will present an extended partially ionized zone that is almost absent in star-forming regions. This is why the collisionally excited lines become more relevant for AGN, leading to higher values of the considered emission line radius. The work from Baldwin, Phillips, and Terlevich was pioneer in the proposal of two-dimensional diagrams to classify objects according to their primary excitation mechanism. The diagram we will be referring to as BPT from now on is this one here, plotted on the right, and we have the axis of oxygen 3 over H beta versus nitrogen 2 over H alpha. These axes individually are reddening insensitive due to the proximity of the line ratios in each of them. And this diagram is sensitive to the abundance of nitrogen with regard to oxygen. We see here the star-forming region that we mentioned earlier, and the objects that are less massive and less metal-rich, more metal-poor, will be here on the top, while the more massive and metal-rich objects will be here on the bottom. And this y-axis is also sensitive to the ionization parameter. The work by Veuillot and Osterbrock refined the proposal from BPT by setting the criteria that should be taken into account when choosing the line ratio of the axis of the diagnostic diagrams. So these criteria are that the lines have to be strong and easily measurable. Blended lines should be avoided since they add noise to the data. The lines in the ratio should be close in wavelength to minimize flux and reddening corrections. They should consider one element, one metal, and a hydrogen recombination line in order to be less sensitive to the metallicity. And at last, they should be in a wavelength range that is accessible with the current astronomical instrumentation. From now on, we will refer to VOS as the oxygen 3 over H beta versus sulfur 2 over H alpha diagram, and VOO as the oxygen 3 over H beta versus oxygen 1 over H alpha diagram. Here we see the VO diagrams according to the original paper. So on the left, we have the VOS diagram, and on the right, we have the VOO diagram. These are the models proposed for Agns, and come back. Sorry. And these are the models for star-forming regions proposed in the Veuillot and Osterbrock paper. And we see that the VOS diagram is sensitive to the electron temperature and also to the density. And both axes are sensitive to the ionization parameter. The VOO diagram is the most appropriate one to differentiate star-forming regions from Agns, but the oxygen 1 line is usually very weak and therefore associated with larger uncertainties. Just a second, I'll take some water. Okay, so the main motivation behind this work is to avoid the ambiguity issue that often occurs when one tries to use the 3 diagnostic diagrams to classify objects, meaning that a same object can be classified differently depending on the considered diagram. Therefore, we propose 4 alternative diagnostic diagrams with their respective classification schemes. Their axes consist of linear combinations of the standard optical line ratios from the BPT and VO diagrams, and we rely both on empirical and theoretical approaches to better constrain the behavior of the objects and the influence of the different parameters in these new diagrams. The classification schemes are empirically based, and they minimize the number of misclassified objects according to our sample. In order to have reliable data to propose our alternative diagnostic diagrams, we were looking for a sample that will be in agreement with the following criteria. It should consist of a large sample with galactic nuclei that are ionized by both Agns and star-forming nuclei. We needed spectra to be in the optical range because we wanted to use optical emission lines. The sample should be complete and uniform, with data obtained with the same procedures and equipments in order to minimize the error and to make a statistical analysis possible. The observed objects should be in the local universe to guarantee high resolution of the nuclear regions. And the data should be open source in order for us to compare our results with other works from the literature. With these in mind, we have chosen to work with the Sloan Digital Sky Survey as DSS to provide us with a large amount of good quality, homogeneously obtained spectra. This survey produces images of the northern hemisphere sky and spectra of over 1 million galaxies. Regarding the spectroscopy, it uses a 3 arcsecond diameter fiber that covers the wavelength range of 3800 to 9200 angstrom, and with a spectral resolution of 1800. This data was obtained with this 2.5 meter telescope, which is located in New Mexico. The sample we have considered in this work was obtained from the main galaxy sample, which is a reddening-corrected R-band magnitude-limited sample of galaxies. This embraces a wide range of galaxy types, but it does not consider galaxies with broad lines such as type 1 Agns, which is good for us because type 1 Agns are already distinguished from star-forming nuclei by the width of their lines. We use the 7th data release since it contains data from all the previous data releases regarding extragalactic objects. And we obtained the data from the Max Planck Institute for Astrophysics and the Johns Hopkins University, the MPA-JHU catalog. We use information such as emission-line fluxes, equivalent widths, and continuum flux densities with their respective errors, redshift, velocity dispersion, and other information that were used to identify the objects, as for example, the position in the sky, the plate, fiber, and photo IDs. Based on this whole sample, we used 2 criteria to define our subsample. So we consider a redshift cut at 0.016 for 2 reasons. The first reason is because since the aperture, the fiber aperture of SDSS has a fixed size of 3 arcseconds, we needed to account for very nearby objects in order to have observations of only the nuclear region that were not heavily contaminated by the outer regions of the galaxy. The value of 0.016 was considered because of the second reason, which is the sulfur 2 doublet shifts into an atmospheric band for redshifts higher than this, which would add errors into our data. The result of this redshift cut is that the maximum diameter of our observations is of about 1 kiloparsec. Moreover, we consider an error criteria of epsilon smaller than 0.1 DAX for the emission line radius in order to select high-quality data and to ensure that the results of this work are robust and reliable. Though we recognize that this kind of selection criteria biases our sample to only strong emitters. As a result, our sample consists of 4,192 emission line galaxies in the local universe. Here we see an example of a galaxy that we use in our sample with the considered emission lines highlighted. This is a star-forming galaxy. Now we will begin to talk about the analysis of this work. This section is divided in 3 parts, which are the traditional diagnostic diagrams, the alternative diagnostic diagrams, and the theoretical models. We have applied our sample to the standard diagnostic diagrams, and we can see here in the BPT diagram this is the BPT diagram, the VOS and VOO diagrams. So mainly in the BPT diagram, we see what is denominated the seagull shape of the data. So here we have the left wing of the seagull, which is associated to the star-forming main sequence, and the right wing is associated to the AGN branch. And the body of the seagull is often associated to transition objects. It is worth pointing out that the retired galaxies will overlap liners in the AGN branch. So we have tested the behavior of the data according to the different classification schemes that have been proposed in the literature. So here in green, we see the empirically based classification scheme proposed by Ho, Filipenko, and Sargent 1997, where they separate both star-forming region from AGN and also safe from liners. And we can see here in the VO diagram that they propose a transition region. The red curves here, also in the 3 standard diagrams, were proposed by Keeley et al. 2001, based only on theoretical photoionization models, and they separate star-forming objects from AGNs, and the lines are referred to as maximum starburst lines. The teal curve here in the BPT diagram shows the line that was proposed by Kaufman et al. 2003, based empirically in the SDSS sample. And later on, Keeley and Kaufman together proposed these blue lines in the VO diagrams to separate safers and liners in the work Keeley et al. 2006. And also in this work, they reinforced the importance of the Keeley et al. 2001 line and the Kaufman et al. 2003 line to define this region in between the lines as the transition region. Earlier in this year of 2006, Stasinska et al. Have proposed this magenta line here in the BPT diagram, which is both empirically and theoretically based, and it separates star-forming regions from AGN. These 2 lines here in the BPT diagram, the orange and the cyan lines, they are somehow similar because they were both based on these blue lines of the VO diagrams proposed by Keeley et al. 2006. The orange line was proposed empirically by Chavinsky et al. 2007, and the cyan line was proposed by C.G. Fernandez et al. 2010 with an optimal transition approach where they basically translated these lines here to this diagram here. Optimal transposition basis. And at last, we have this purple line here, which was proposed by Melendez et al. With a theoretical basis, but with the main focus on infrared lines. And we see that it is a bit different from the shapes obtained with the approaches that were based on optical lines. In our thesis, we have discussed each of these classification schemes, and it's important to check on the visual plots because we do not only want to know how many objects are being misclassified, but also where these problematic cases reside, in order to understand if the objects are atypical themselves or if there is an issue with the classification scheme. However, we will skip this discussion in this presentation and we will focus on the main result. Since we wanted to classify all the objects in our sample, we have chosen a classification scheme that is based in a single diagram, which is the BPT diagram, the most commonly adopted standard diagnostic diagram for representing the strongest and easily measurable emission lines. This straight line here was proposed by C.G. Fernandes et al. 2010, and since this classification scheme is based on the lines proposed by CLOUDY et al. 2006, we have maintained these curves from this work, recalling that actually this line was proposed by CLOUDY et al. 2001, and this one by Kaufman et al. 2003. Therefore, from now on in the presentation, we will present the star-forming nuclei as green data, the transition objects in black, Seyferts in blue, and liners in red. We are showing also the CLOUDY et al. 2006 lines for the VO diagrams, but we have not considered them in our classification and color code. We are just showing them for a comparison. And we have chosen this classification scheme because it was the one that shows less ambiguity for the objects in our sample. We also provided a discussion about these transition objects shown here in black. And these galactic nuclei, they present spectral features of both stellar and nuclear photoionization. That is often associated to low resolution of the data, both spectral and spatial. And the theoretical models don't help us much in solving this problem, since the region can be populated by objects with pure AGN emission, pure star-forming emission, only hot old stellar populations, with the contribution of shocks, or even by the nature of these different models. Hence, the dominant ionization source in these objects is rather dubious, and that can reflect intrinsic properties of galactic nuclei with more than one type of ionizing mechanism acting simultaneously. In some cases, we could also be witnessing the effects of AGN feedback that can quench or enhance star-forming episodes. It is important to check aperture effects since we are considering a fixed size lith, and further galaxies will present more contamination of the circumnuclear regions to the integrated spectra. However, in the case of our sample, we have tested it, and there was no trend on the classification observed with increasing redshift. High spatial resolution, as the one obtained with integral field unit data, would be required to check on how much of the circumnuclear H2 regions might be contaminating the spectra of bona fide AGN. We must emphasize that not all transition objects will have the same explanation and be explained by the same composition of ionization mechanisms. Therefore, we decided to maintain this class when analyzing the alternative diagrams in order to evaluate their ambiguous behavior. The issues of objects that are classified differently in the three standard diagrams can lead to insights about the nature of such objects and/or about the fineness of the classification scheme. Some of the extra ionization sources that might be contributing to the observed spectra are shocks, and these shocks can be due to stellar processes, AGN feedback, and/or to galaxy interaction, or it can be associated to diffuse ionized gas and post-AGB stars. Some concerns related to the data quality, as we mentioned, are the aperture size, because this can add extended emission to the integrated spectra, and therefore there will be And moreover, there will be some difficulty when we try to measure very weak and faint lines. Another possible explanation for the misclassification events is a dubious dominance of the different ionization mechanisms that might be acting simultaneously. Some of the spectral features that can help us to define the main power source of these objects when the optical emission line ratios are not enough is the equivalent width of H alpha and the break at 4,000 angstrom. For using these lines in diagnostic diagrams, we recommend the one diagram proposed by C.G. Fernandes et al. 2011 and the DIU diagram proposed by Stasinska et al. 2006. We also emphasize that the classification scheme proposed by Keeley et al. 2001 for the VO diagram seems to be too strict, with several star-forming nuclei lying above the proposed boundary line. Okay, so now we will present the alternative diagnostic diagrams that are proposed in this work. They consider linear combinations of the standard emission line ratios. So the difference between the oxygen line ratios is useful to constrain the ionization level of the sources, considering that the Balmer decrement shown here does not vary much to our sample. The sum of the oxygen line ratios and also the sum of the nitrogen and sulfur line ratios will be sensitive to the excitation temperature. The difference between the nitrogen and sulfur line ratios results in a ratio between nitrogen and sulfur that is independent of the hydrogen recombination lines, and this is sensitive to the metallicity and to the ionization level. We use all the standard emission lines simultaneously in order to consider all the information available in the traditional diagrams, minimizing the ambiguity issue. Though we think that it is important to consider more than one diagnostic diagram for the objects that lie near the boundary lines proposed. We are aware that the requirement of all the measure lines can bias our analysis to strong emitters, but since we do not wish to propose a demographic study of all galactic nuclei, we have chosen to make this analysis with data that exhibit reliable measurements. This first alternative diagnostic diagram uses the sum of the line ratios in its axis, and it has a similar shape to the standard diagrams. Objects with harder radiation field will be positioned to the upper right, while the star-forming sequence can be seen here in the lower left. We are proposing a rectangular hyperbola to separate star-forming nuclei from AGN, and we can see that it does not follow the star-forming sequence closely, because we wanted also to embrace some of these transition objects and some of these objects with larger error bars. We also propose this straight line to separate the two types of AGN, liners and Seyferts. This alternative diagnostic diagram is useful for defining a transition region between the star-forming nuclei and the AGNs. For that, we have set two rectangular hyperbola, and our criteria was to have the minimum number of misclassification, meaning the lowest possible number of star-forming nuclei and AGN inside this region, though we see that outside of it we have several transition objects. We think that this might be an indication of the dominant ionizing source of these objects here. This plot distinguishes the classes according to their excitation temperature, and we can see that it is not possible to distinguish the two types of AGN. If an object lies in this transition region, we recommend to check the position of this object in the other diagrams in order to determine its main ionization source more clearly. The ordinate axis of this alternative diagnostic diagram gives important information regarding the ionization parameter, considering that most of our objects lie in a rather small range of Balmer decrement. The difference between the twice ionized and the neutral oxygen emission lines was used to distinguish Seyferts and liners when Heckman in 1980 first defined liners. We have tested the suggested separation between such classes, but we found better results by proposing this straight line here to differentiate liners and Seyferts. And the separation between star-forming nuclei and AGN was made as usual with the rectangular hyperbola. This diagram here was already used in several works from the literature to estimate the metallicity of objects, and we emphasize its importance in galactic nuclei classification. It is very economic since it considers only emission lines that are nearby in wavelength, and that makes it more inclusive for galaxies that present weak or absent oxygen and or H-beta lines. And also, it's relevant for observations with limited spectral coverage. We have proposed a scheme to separate star-forming nuclei, Seyferts, and liners, but after our analysis, we find it more robust to simply separate star-forming regions and AGNs with this line, which emphasizes the importance of the oxygen lines to distinguish between high and low ionization AGNs. It is important also to highlight that in this diagram, we have Seyfert galaxies lying nearer the star-forming sequence than the liners, which is not typical from the diagnostic diagrams. And this is due to the fact that this diagram is more sensitive to the metallicity and therefore to the mass than to the ionization parameter. So in that sense, the Seyferts that usually reside in the green valley will be lying closer to objects from the blue cloud as the star-forming regions than liners that usually reside in the red sequence. Now we will talk about the last part of the analysis, which is associated to theoretical models. Theoretical modeling is important for us to understand the influence of each parameter to the position of the objects in diagnostic diagrams, and also to constrain probable values of such parameters, though the models necessarily include several simplistic assumptions that do not always represent well the complexity of photoionized nebula. The stellar spectral energy distribution considered in this work was generated with Starburst99, where we have set an initial mass function according to Krupa 2002, the star formation rate of 1 solar mass per year, the stellar atmosphere formulation as proposed by Poldrach and Hillier, and a continuous star formation history. And we also use all the available metallicity values of the Geneva standard tracks to then produce a synthetic spectrum, which can be associated with a determined age of the stellar population. The results shown in this work refer to the age of 10 to the 6 years, since they provide harder spectra than older ages. we also emphasize that this code considers simple stellar populations, since the analysis by D'Agostino et al. 2019 has shown that though binary systems can produce harder spectra, the differences in the resulting emission line ratios is rather small. The same can be applied to not including supernova remnants. So here in this plot, we see a comparison of two of our simulated spectra. In blue, we have our lowest metallicity, 0.05 solar metallicities. And here in red, we have twice solar metallicity. Once we have produced these stellar SEDs, which are one of the input parameters, we are considering the photoionization models using CLOUDY, which is a spectral synthesis code that is able to simulate the ionization, the chemical, and the thermal states of a material that is being exposed to an external radiation field. The main inputs of this code are the geometry and thickness of the cloud, the composition regarding metallicity, dust, and ionization, the density, and the radiation field, which is associated to the SEDs. The output will be the simulated spectrum. In the thesis, we have a proper description of each of the relevant inputs that justifies the choices of the values we have adopted. Here I show figure 1 from Feltri et al. 2006, where we see a comparison between the SADs of two stellar populations and of an AGN, with this energy of relevant transitions shown as black lines. So this gray shaded area indicates the location of AGN ionizing spectra with a power law index between -2 and -1.2. The blue spectra is associated to a 0.05 solar metallicity value, and the orange spectrum is associated to 1.5 solar metallicity SED. This shows the main difference between the photoionization models, since the stellar populations do not emit in energies greater than about 50 electron volts, while AGNs do. In this table, we show the values and considerations we have adopted in order to run our models. So we consider constant densities that are higher for AGNs than for star-forming nuclei. We consider the same wide range of ionization parameters for both types of objects, and then we rejected those that did not show realistic results. The adopted geometry was a plane parallel open geometry, and the filling factor was of 1%. The stellar SED was generated with Starburst99, as already mentioned, and for the AGNs, we have considered a power law with varying spectral index for the slope from the UV to X-rays. The metallicity of the star-forming nuclei was said to be in agreement with the available Geneva tracks, and we have set similar values for the AGN, focusing on higher metallicity values. We set the dust to be proportional to the oxygen abundance and also changed the default abundance of elements usually associated with dust in star-forming nuclei, where for simplicity we did not consider dust or abundance specifications for AGNs. I apologize that I'm talking faster, but my time is running short, so we have to run a little bit, okay? Then you can ask me later. So the nitrogen abundance turned out to be more important to constraint than we originally thought, since only after setting an appropriate expression we could have reliable models regarding our observed sample. So nitrogen can be produced primarily from elements that were produced inside the star, in a process that does not depend on the initial chemical composition of the medium from which the stars were formed. Therefore, for lower metallicities, we expect nitrogen to be independent of oxygen, as shown here by this constant dashed line. However, nitrogen can also be produced in a secondary origin as a product of elements that existed prior to the star and therefore being dependent on the history of chemical enrichment of the surrounding ISM. In this case, there will be a dependence between nitrogen and oxygen abundance, as we see in this pointed line here in this abundance graph. Hence, it is important for us to understand how this dependence occurs and how is the transition between the two origins of nitrogen in order to produce reliable models. We have tested several equations for the dependence of nitrogen abundance with regard to oxygen. And in our final models, we have considered this proposed equation with a second order term here to best fit the expectations for higher metallicities. And it was based on the match between our simplistic photoionization models and the observational data from our sample. It is important to emphasize that galactic nuclei tend to be more metal-rich than the outskirts of the galaxies, so this equation might fit better for these star-forming regions, but not be the most adequate for H2 regions in general. So here we find a comparison of several nitrogen abundance equations that we use from the literature, and our proposal is this one in dark red. Okay, so once we have explained how we build our photoionization models, we can then apply them to the diagnostic diagrams. It is important to apply them to the standard diagrams first, to then apply them to the alternative diagrams to see how these parameters behave in the new dispositions. Here we see a grid of our models in the BPT and VOS diagrams that cover almost all of the data for star-forming nuclei. This region here that was not covered could be achieved with models that consider maybe harder ionizing spectrum, higher density, and or higher metallicity. And we can see that the two main parameters for describing the star-forming sequence are the metallicity and the ionization parameter. Okay, here again we show the BPT and the VOS diagrams, but now without a grid and showing only single plot points to represent some average values that we have chosen. So we see that liners are well explained by higher metallicity objects in this case, and in this case by lower ionization models, which is in agreement with what we expected. And we see that the star-forming region is well reproduced. However, our models do not adequately represent the neutral oxygen for either types of objects, and we see a trend of lower values for the abscissa than we expected from our sample. This is probably due to the fact that the partially ionized zone where such ions were emitted present different conditions of density and ionization parameter from the regions of intermediate ionization, where nitrogen-2 and sulfur-2 are also proposed. Because of such discrepancy of the modeling of neutral oxygen, our models will not fit the data well in the alternative diagnostic diagrams that consider such line, but they can still provide us information of how the parameters behave in general. So in the case of this alternative diagnostic diagrams, the Agn models are not so discrepant, but we see the systematic deviation from the star-forming models. And we see here that this diagram is very sensitive to the hardness of the spectra, as we see by the distribution of the colors here. And we also see that we have a higher metallicity usually associated to liners and lower metallicity to safewords as expected. In this diagnostic diagram, we also see the deviation, and we see that this point here lies closer to the star-forming sequence than the Agns as it should. But we again see that the AGN models are rather representative of the data, and flatter spectra tend to be more to the lower right, but this trend is not as explicit as in the diagram with the sum of the oxygen line ratios. And here we see that lower metallicity tend to be more to the left than higher metallicity, which is adequate to this line that is sensitive to the metallicity. We also see that this diagram is sensitive to the ionization parameter with a trend of the colors here and here. Considering this economic diagnostic diagram, we see two trends for the metallicities, mainly of the Agns. And we see that since it does not consider the oxygen line, the star-forming sequence is being well reproduced. In this case, the star-forming models and the Agns also lie closer, and we think that this is also associated to the fact that no oxygen lines are being considered. Okay, so sorry, a little running out of time. To summarize our results regarding the theoretical models, though we have attempted to reproduce most of the optical line ratios with success, the underestimation of the neutral oxygen line makes the models inadequate to the alternative diagnostic diagrams that consider this line, showing systematic deviations. And this issue is not new and has been faced by many simplistic photoionization models. And some of the possible solutions include considering harder radiation fields, as for example, by adding shocks, setting higher temperatures, or including extra sources as Holmes, Dig, and cosmic ray heating. Or maybe we could consider higher densities or the inclusion of dust. We have tested some of these things as higher temperatures and shocks, but we have better results when we combine different densities, though sometimes when we fix the VOO diagram, we had issues with the other two traditional diagrams. So we think that combining models with different values of densities would be an interesting approach. And we explain a bit of this in the appendix, but this adds so many free parameters that it gets harder to really constrain the realistic values of each parameter. Therefore, we conclude that it's very complex to model different lines emitted by photoionized nebula, since these lines will be emitted in different regions that have different conditions, and they trace different information regarding this nebula. But we do conclude that single density models are too simplistic, though they can still provide us insights about the use of alternative diagnostic diagrams. And now to the conclusions of this work, we have proposed a review of the main diagnostic diagrams and classification schemes. We recommend the use of Keeley et al. 2006, differentiating between star formation and AGN, though we think that the VO diagrams might be too strict. And for the Seifert and Liner comparison, we recommend Sigfrids et al. 2010 classification scheme. We have proposed alternative diagrams with 3 of them with linear combinations of the 4 emission line radials used in the standard diagrams, and one economic alternative diagnostic diagram. And we also have proposed classification schemes that were derived from such diagrams, minimizing the misclassification issue. And they are successful at separating the classes of galactic nuclei neatly, but these diagrams are based on the same line ratios than the standard diagnostic diagrams, so they are not able to discern, for example, shocks, old stellar populations, or diffuse ionized gas. So even though they are useful for avoiding ambiguity issues that can affect the use of 3 traditional diagrams, objects that lie close to the boundaries should be analyzed individually, and parameters such as the equivalent width of H alpha and the break at 4,000 angstrom might be useful for their classification. Also, though the taxonomy is very important for us to better understand galactic nuclei, these objects can be very complex and simultaneously harbor multiple ionization mechanisms. So these classification schemes are a simplistic approach for defining the dominant source. We also have proposed theoretical models, and we see the main parameters that determine the position of an object. And these models are very important for constraining how each parameter affects the position of an object, but they rely on several assumptions, and we cannot precisely estimate the values of the parameters from the models. We have also shown that single density models are insufficient to describe the complexity of photoionized models, and these models, these objects in nature, they actually have complex structures and show gradients in density, temperature, and ionization parameter. We have also proposed a new equation for the nitrogen abundance with relation to oxygen in star-forming regions that might be biased for the higher metallicities of galactic nuclei. And for our future perspectives, we want to keep on studying galactic nuclei, but at higher redshifts, and we want to apply these diagnostic diagrams and classification schemes to determine what changes in these objects according to the evolution of the universe. And this work can be particularly useful for all of these telescopes that are shown here. I'm sorry I'm out of time and I ran, but that's it. Thank you very much.
Thank you very much. You are exactly 60 minutes. Thank you. We now proceed to the evaluation by the committee members. And I would like to thank again the participation of these distinct committee members here, Dr. Montse Vilar Martins, Olidos, and Walter Maciel. We start with Montse. Could you go ahead? Thank you so much for being here.
Sure. Let me take the time just not to go over my time either. Well, first, congratulations, Catarina. I'm really impressed with the work you've done. I think it's a very complex project with so many concepts to understand, so many parameters on the modeling that make it, to me, I think it's very, very difficult to really interpret what you can extract from these diagnostic diagrams with so many ideas involved. So I think that you have gained a huge amount of useful skills, both from using models to predict the line ratios of different types of objects, the theoretical understanding, also the issues that could affect what we are looking at, like the size of the aperture that you explained very well. So I think that you have put together an excellent work, very well structured on the thesis you have written as well, which is not trivial at all when there is such huge amount of things to take into account. So from my personal perspective, congratulations. I think that you have done an excellent work.
Thank you very much.
So I have some questions as well, of course. The first one concerns the spectra you have used from the Sloan. I take for granted that you have subtracted the stellar the absorption. I know you mentioned it, that it is important to subtract the stellar continuum to correct for that stellar absorption. Can you confirm that you have, well, this was applied to the spectra you have used?
Yes, I was not the one who did it, but when we use this MPA-JHU catalog, they have already subtracted the stellar features, and then the emission lines that they provide the values already account with this correction.
Okay. Then a simple question is, looking at the diagnostic diagrams where you have measuring to H alpha, what seems clear is that any object that has natrium to H alpha below minus 0.6 roughly in log, that's a star-forming object, right? That's a clear diagnostic that emission-line objects with such low natrium to H alpha for sure they are star-forming objects, right? I think that's something clear, right?
Yes, this was this distinction of star formation and AGN only by the nitrogen line ratio was proposed by Stasinska et al. 2006. And in the analysis I do of this classification scheme, we see that it is very useful. And they also define a transition region between those. So I applied this to our diagram, and it really seems it's a good economic approach, because when we consider the oxygen lines, then we see that there are some cases of objects that are probably safer with low metallicity, so they will have low nitrogen over H alpha, but they still have somehow a high ionization, so they will have a high oxygen over oxygen 3 over H beta. So as a simplistic approach, it is very useful, but still I find it better to use more than one emission line ratio.
Okay. Regarding the transition objects, what seems clear is that it seems to me that you need more information. I mean, whether it is X-rays, radio, or higher spatial resolution, as you say, to be able to concentrate more on the nucleus. But it seems to me that these lines are just not enough. So do you know if it has been done for some of the objects that are classified as black dots in the transition region, whether it has been checked what they really are by taking other sources of information, for instance, X-ray. If they are very bright on X-rays, that might be pointing to at least a quite predominant AGN. So I don't know if someone took care of that type of check.
Yes, if we look at them in other wavelengths, this sure helps, but let me show you an extra slide here, because my group, they work with data. Just a second, let me present here. They work with IFU data that is still on the optical. So what we were talking about, the higher spatial resolution, right? So this is an object that is traditionally classified as a transition object. And what we have here when we analyze it on IFU is that the central region is associated to AGN emission. And we have this kind of a ring of star formation. This is from Patricia da Silva work from 2020. And the comparison that they have been doing is considering the Palomar survey, which is a survey on the northern hemisphere that considers the nuclear regions, but with integrated spectra. They are analyzing objects in the southern hemisphere with this higher spatial resolution. And when they classify these objects, they have much less cases of transition objects than what was seen by Ho and collaborators. So we do see that many of these cases, it is an issue of having multiple mechanisms of ionization that in the integrated spectra are really messed up. But I think that with the new facilities, also the extremely large telescopes that are coming and these kind of information, we will be able to disentangle this transition object issue even better in the future, nearby future, I hope.
Okay. So, so if when you compare the data, the location of the objects with the models, where you consider the ionization parameter and the metallicity on the different sequences, my question is, a given object, I mean, one of the issues is to try to reproduce the sequence in the in the different diagnostic diagrams that you investigated, including the new ones you proposed. Now, the other issue is up to what point can we use this methodology to constrain, for instance, metallicity? So this means, for instance, if you have an object that in a given diagram is reproduced by, I don't know, have solar metallicity models, is this coherent in the other diagrams? I mean, can the same object be inconsistent with the in the models in the 3 diagrams? Do you need have solar metallicity in one diagram and twice solar in another, for instance?
Mm-hmm. Well, I think that regarding the star forming sequence, this is easier than regarding the AGN, that sometimes the models get more messed up. But still, I used to think that the photoionization models were very reliable until I ran them. Because then when we do it, we see the amount of simplistic assumptions that we have to consider. And then we always get kind of like, it is, my impression is that they are more useful to see the influence of the values of the parameters than to really constrain a value by itself, because sometimes you can be modeling, like you have a consistency in the diagrams, but with models, for example, 0.5 solar metallicity and a high density, or a high metallicity and a lower density, combinations like this can sometimes result in objects that will have similar emission line ratios. So okay. I think that for us to say, this object probably has this value of metallicity because of the photoionization models, I think it's better to use the observational information of the spectrum.
Okay. So a question that, well, it's a bit to see how you can improvise. Imagine that you have to model the emission-line spectrum of a nebula that has been ionized by population 3 stars, primordial stars, the first generation of stars. So imagine that now in spot I ask you, okay, what parameters would you consider in terms of metallicity and density for the nebula, and how could you characterize in a very simple way the ionizing continuum of these stars?
Yeah, that would be a little hard because, population 3, there will be kind of no metallicity, right? So mainly hydrogen and helium. So this would be one issue. And I think they would be also much hotter and short time lived. So a hard spectral radiation field. And also, I think that also higher densities than what we observe. Well, the conditions will all be kind of much more extreme than we would see now. So I think that actually the main difficulty would be that we have to rely on this stellar tracks of evolution. And these tracks are not thought to be for population 3 stars. So I will have to go more to the basis of the models than to just use what is available on Starburst99. But I think mainly that.
Yeah, but that's a bit the answer, no? That you have low metallicity, very, very hot stars with a much harder continuum. That already gives you some hints on how you could approach it on a very simple exercise. Then, of course, there are sophisticated spectral energy distribution that have been created already, published, etc. But just as a starting point, that's a very good guess. No, a much harder continuum. So I have no
just something that I wanted to show you on an extra slide, if I can, because it's a work that I hope we can do it together in the next few years. So let me find it here. Sorry. Okay, so this is our proposal with Roderick as a PI. And the idea is that when we observe these more extreme environments in higher redshifts, if we apply them to the diagnostic diagrams that were originally thought to the local universe, we can use this same emission lines that have been redshifted to the near infrared to then compare exactly these parameters to see how the different hardness of the spectra and lower metallicities and higher densities will act on shifting these objects in comparison to the objects that we were seeing in here in the local universe. So these are kind of the main goals for the nearby future.
Yeah, that'll be really exciting, of course. So I have no more questions. Thanks and congratulations again.
Thank you very much, Monse.
Mm-hmm.
Thank you so much, Monse. Thanks a lot. And we'll now go to Dr. Oli Dawes for his evaluation. Go ahead, Oli.
Is Oli speaking? Because I'm not hearing.
Okay.
Your microphone is muted. Strange, because it was working before.
It's open now?
Yes.
Okay, it's very strange.
Perfect, thank you.
Okay, again, thanks for the invitation and congratulations for the very nice work. I'm happy you finished the master. And I know Catarina for 3 years, and I have seen that she is a good student, and congratulations, Catarina and Claudia, for the very good work. I have some questions, some comments, which you take, I think, my 30 minutes. Okay, let's see. I know this subject is very studied along the years, and you look in the literature, you find more than 100 papers about the subject, and I know it's difficult to produce some new diagrams because there are many students in this subject, and I think you got that. You propose a new diagnostic diagrams that it's possible solve some problems in the previous one. And this is a general comment, okay? And about the photoionization models, I think this new relation between the nitrogen over oxygen versus the oxygen, it's interesting results, mainly because it's possible to test stellar stellar products in the high the high metallicity environment. But this new relation it's necessary you compare with another ones. Are you talking that in the along my questions? Okay, I have some particular questions that I list in a table. Firstly, I think, at least for me, the text is very long for a master thesis. I don't know if it is common in USP or in the ON, but when I received the text, I opened the file and I don't believe there are more than 200 pages. Because that I told you, for me there are two theses in one thesis. Okay, but are you not request you summarize more? Because if you wrote a short thesis, people speak, oh, the text is very short. If you write a long text, people speak, oh, it's a very long text. So no, it's okay for me, but like a comment, for me, it's a long test. It's difficult to read it more than 200 pages. And now you repeat some things along the text for me. I read all the text and I will send you my corrections. Okay. And you see I cut some parts of the text, but these are suggestions. Okay, okay. This is my first comment. In the introduction, I think in your presentation you put some image of H2 region and the AGN, but I couldn't see this image in the introduction. So I suggest you put an image of a starburst, for example, image of AGN, in order to illustrate the introduction. I think this is useful, or this get the text more beautiful. Okay, because the introduction is very
a high density introduction.
high density introduction and the descriptive in the I wish to see some image in order to become it no it's a hard text, for example. Okay, let's see. Okay, in figure 1.2, I don't know the page. You show this picture in the presentation where you show the representation of H2 region. Could you put it in the just share this picture?
Yes, just a second.
I will send to you a new picture better than this picture. Okay. I think it's third slide. I don't know.
I'm going to show in the text in case you want to comment something about it.
Okay.
This one, right?
Okay. this for me, it's not a big representation. It's not a good representation of H2 region, mainly because you don't see the transition between hydrogen plus and hydrogen neutral, and here the oxygen plus 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 is almost in the same place that's the oxygen plus. I will send you a new figure better than this figure, because this figure for me it's not good. Okay, just a comment. Now, in the page 39, you speak thermal electron. Could you define thermal electrons for me? It's a question that I know the answer, but just to see.
Okay, so I won't explain it as you want me to explain it, but the idea of the thermal electrons are those electrons that they heat the nebula. So by their kinetic energy, for example, there is an electron with a determined energy, and this is recombinated by an hydrogen. So the atom will use the amount of specific energy to make the transition, but there will be an accident energy that will be released in the form of thermal energy. So I think that's what we refer to when we talk about the thermal electrons, or the electrons that add thermal contribution to the nebula.
Okay, no, because the H2 region, it is not in thermal equilibrium, but the free electrons are in thermal equilibrium. Okay, just you see. Okay. Okay, in the page 42, you report the broadline regions have a higher electron density than the narrow line regions. Okay, and you cite Binet et al. Okay, this I have seen along the text, for example, when you write, for example, the stars are hot, but you don't put the typical temperature. For example, the gas, the Agns have a high electron density in comparison to H2 region, but you don't put the values. This is missing in the text, and I point that in along the text. Okay, but about the board and the narrow line region, about this part of the text, you reported, okay, again, the borderline region, in borderline region, the electron density in the gas is higher than the narrow line region, and you cite Binet et al. First, what is the typical value of the electron density in broadline region and the narrow line region? You know that. It's a question.
Yeah, I know more or less. I have it in the part of the models. I give this values more accurately. The narrow line region can go from, I think, 10 to the 2 to 10 to the 4 centimeter per cubic centimeter.
Perfect, yes.
And the broadline region I have studied last, but I think maybe 10 to the 6.
Yes, it is about 10 power 4 and power 6. Okay, but when you cite Billet et al., uh, how I suppose this value are in this paper, okay, but how uh, was calculated the electron density in the borderline region? This is a question because it's
Yes, I
not
have to
possible.
check because it's not the ratio as in the narrow line region, right? The
Yes,
sulfur or
yes,
oxygen rate.
yes,
Yeah.
yes, yes. Uh, I, I speak that because it's not possible to measure the density using the sulfur lines, the argon lines, the modern region. Okay, probably in this paper, Ability wrote, because the narrow lines are supprimidos, I don't know, suppressed, something, but it's not possible measure directly using optical lines the electron density in borderline lesion. Okay, so take care because if you later read this sentence, he or she can think in Billet et al. Then measure the electron density in the body, the narrow, uses some method. Okay, okay. Following this same direction, in the page 48, you see that values similar to 10 power 4 are derived in H2 regions. Okay, but if you read in the next page, you see the paper of my ex-advisor Copete. Typical electron densities in H2 regions are 100 or 200. But in this page, in particular, you write values about 10 power 4 are derived in H2 regions. I think it is not correct, or I don't know. Please,
Yeah, I'll have to check the rest of the paragraph to see if I'm talking about, for example, starbursts that might have higher densities or more extreme values. But when I
okay.
talk about 10 to the 4, it is probably like the highest density values that we can reach with that have been observed to an H2 regions. But the typical average values
Yes,
are
I
these
know.
ones of 10 to the 2. Yeah.
Yes. This because I read many papers about electron density and the regions, and I never found these high values because that I see this sentence when in this sentence it is missing the citation or the paper where this high value was found. So when I send you uh, my corrections, you can see if this is real or not real. Because if you write 200 pages, it's possible you make some mistakes. Okay, okay. Just see. Okay. In the page 5, 6, you point that it's better. Of course, this is true. You cite it's better use lines ratio lines in the diagnostic diagrams with near wavelength in order to avoid the problems in the radical correction, in the flux calibration. Okay, this is true. But uh, uh, what are these problems in the radical correction in the flux calibration? You don't write this problem produced in the radical correction or in the flux calibration. I don't know if you understand my question.
I didn't check on these issues that could appear, because I think that this consideration of the wavelengths being close was proposed in 1987. So ever since, most of the diagnostic diagrams already consider lines that are close. So that's why I didn't really explore this issue.
No, okay. I know, but what the question is, if you have a line ratio, for example, in the blue, for example, oxygen 3737 and the nitrogen 684, I don't know. If you take this ratio in a diagnostic diagram, you have problems with the, because this line are because this line don't have near wavelengths, and you suffer effect problems with the radical correction. First, what is this problem?
Okay, so first we will have the error bars being larger. And the problem with the reddening, I think that like I can only think of larger error bars, because when you get two lines that are too separate, the way you can measure one line and do this considerations of how much it is being affected by dust, it will be different from the other one. So I don't think that this will have like a systematic effect in the diagnostic diagram, but each line when combining the ratio will have higher error bars associated. So this will make it more difficult. If you have higher error bars, then sometimes the same object can be classified differently, because the error bars are considering more than one of the loci of the diagram.
Okay. I'm a theoretical astronomer, but no, and I don't know what is the problem in the flux calibration in lines with very different wavelength, for example. And this is not mentioned in the text, for example. You write, it's better use lines with near wavelength in order to avoid the problems with radical correction and the flux calibration. Okay, but you don't write what, which are these problems. Okay, so just to you can do that after asking for the people. Okay.
Yes, I mean, for example, when you have two lines that are close together, if you do a reddening correction, for example, right, to correct dust, that is not very much appropriated to that object, let's suppose that you do it incorrectly, at least it will be equally incorrect for both. So when you do the ratio and you combine them, this will not affect the lines. But if you do something wrong, or not even wrong, but if you have different procedures to do the reddening correction for a line that is more red compared to the other that is bluer, then this will add more uncertainties to your data.
Yes, you know, you have to assume some curves of Cardelli extension or another one, and it is produce some uncertainties in the radical correction. Maybe you can write some things in this direction. Okay, but about the flux calibration, I don't know, because probably Roderick and Claudia can be help you answer this question, but I don't know, because I'm meteorological. But probably no. I'm sure there are problems in the flux calibration in lines with a high different wavelength. Okay, just you put a paragraph after uh, after you sit this problem. Okay. Let's see. Talking about the Baldwin-Phillips-Terlevich paper, in the first paper. Okay, they consider just one diagram, and they define it. This is H2 region. This is AGN, and this is planetary neighbor. Okay, some people call it the planetary nebula biliner, but not. You speak correctly. These curses are planetary nebula, no liners. Okay, but how? Okay, Baldwin. Let's see my question. How did Baldwin know that the AGNs are really AGNs? And
Yes,
and the H2 regions were really H2 regions. This is this is very important, because you base it on your working in this.
yes.
Okay.
Yeah, I think it was the other way around. So they selected from the literature works that have been analyzing H2 regions and planetary nebula and AGMs, and then they used this spectra and plotted the diagnostic diagram with the objects already pre-selected as they were. And based on that, they would see, oh, this diagram is good for separating these and those. But it's also important to emphasize that on the BPT diagram, the BPT paper, they do not propose only the BPT diagram. They use the oxygen the oxygen 2 line several times in several diagrams, and this line was not very much used since Veilleux and Osterbrock set this thing of lines being close in wavelength due to reddening problems. So I think that the main answer for what is this issue of different wavelengths will be in this Veilleux and Osterbrock paper. And in these different graphs, some of them they can see, oh, for example, in this graph, we are able to separate also planetary nebula from H2 regions. In this graph, they are more in the same region, and so on. But the objects were classified a priori to the diagrams.
Probably they know the AGNs are a variability in the X-ray, in this sense. Okay, they were sure that these objects are AGNs, of course. Okay.
Yeah, we have to check each of the reference that they use.
Yes,
for
yes, certainly, because there are previous papers that Baldwin Phillips Terlevich based on the classification, because okay. It's important, I think, you put in the text.
Okay.
You put in the text. I don't know the answer. Auger process. You know that? I'm sorry, but
No, you are right. I don't know what that means, and it is in the manuscript that I sent you. But when I was doing the revision, I looked at it and I saw like this is the only thing I do not know how to answer, and I do not like I didn't even see in my radiative processes subject, so I removed it. I just have taken it because it was one of the descriptions in the Ho et al. Paper, the annual review from 2008. So it was there as one of the characteristics, and I put it there. But I'm not confident about what this Auger process means, and I don't think that many of us are either. So in this version that I'm going to submit to IAG, I have removed this part.
Yeah, I'm happy because I don't know, and you don't know, and what is that? With you answer to Catarina, but I don't know. Of course, I studied the Osterbook book, but or I don't remember, or I really don't know. It's the same. Probably Marcel can be help us, but just you know, it's very dangerous. You put something in a text in which we don't know explain because see, I did this question for you. Please explain this Auger effect. And you can, I don't know. Okay, this is it's sometimes it's very dangerous. You put okay, Catarina. I'm finished. I have a couple of questions. Are you using my 30 minutes that Claudia gave me? Okay, just a comment. For me, in the motivation, it's missing. You put two things. Okay, my last talk with Steiner, unfortunately, was in the Bento Gonçalves, and he called me, only sit at this table, and let's talk about the Catarina paper. It's good you remember this thing. And he told me, I know this subject, it's very studied in literature, but we select lines with small error bar. Okay, this is the great deal of the work as well. For example, people select the data with the lines with error in 50% of the measure, and you select only the good lines. Okay, I think this is important that you put that in the motivation. Okay, I just are talking what Steiner told me. Okay, please put that in the.
Yes, it's just that although they are high quality data for the Sloan Digital Sky Survey, I am not very sure about calling them high quality data because it's still regarding to integrated spectra, which is now comparing to IFU technology and so on. It's a medium quality, I would say, but I will emphasize that in the range of medium quality, it's the best quality we have.
And he showed me looking only the bar are very small. This is very good. This avoiding misclassification, and very good. And when I read your text, this was not there in the motivation. Please put that. Okay, Claudia. I have more than 5 minutes.
Of course, you leave.
Okay.
As a guide, I'm sorry if I understood it was something written on stone. It's not at all.
No.
Go ahead, because you have to feel satisfied that you have asked everything you want. So please go ahead.
Okay. I'm finishing. Are you sending to Catarina my correction, my answer,
Okay.
more text that I produce in order to improve the text? Okay. Okay. Catarina, you put in figure in page 118, and fortunately you show this picture where you show in the x-axis the H beta per H alpha. Could you put this figure in the screen? It's not clear for me this picture is that.
Sorry, let me just unmute and then I go back.
I'm muted?
No, I was muted.
Okay. First, in all the label of the pictures or in most part of the label of the pictures, it's not clear if this sample is your sample. Okay, it's important you put in the label of this plot and the another one, the points the points are your sample described in the section blah 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 blah. Okay. In particular, this is very interesting picture because I don't know if it is data were corrected by reading because in general, after you corrected the data for reading correct or for dust presence, you found the values between 2.8 or 3.2. Okay, and now I can see H alpha per H beta reaching up to 10. I don't know if in this plot the data are not reading correction.
Well, the reddening correction, as much as the starlight correction, they were done by the catalog itself, the MPA-JHU. So I just used the values that they give for the emission lines and etc., already expecting them to be corrected. But you are right. This diagram, it doesn't make me very confident about this theoretical value, right, of 3.1 that we expect. It's from Osterbrock, because we see that though I think most part of our sample is in this range, we do have many objects that are not. So we'll have to check.
You have to check it because if you divide the H alpha per H beta, if its value is not correct, it's not already correct, you will find a low values. Okay, probably in this plot, this point are not already correct. It's impossible you read correction and you find 10 for the H alpha per H beta. Okay?
Yeah, because usually you do the reddening correction based on this value, right? So yes.
No, it is impossible. Probably you are showing something and you are speaking about another one. Okay, check this plot because there are something wrong.
Okay.
Okay. let's see. Okay. Okay. When you consider first thing, when you have been at when you sum the log of aligning ratio, for me it's a little strange because, for example, the sum of the log of nitrogen per H beta plus sulfur per H alpha is the same. You multiply the line ratio, for example. It's a little strange, but I have to check if more people use that, or you use that. It's not a problem. But okay, in particular, in the figure 3.5, in the page 123, you using the X in the abscisses, the ratio nitrogen 2 per sulfur 2. Okay, and you write, okay, this line ratio is dependent on the metallicity. No, if you put some plot in the presentation, this one alternative one plot where there is the vertical, the oxygen 3 versus
over H beta.
Multiply by oxygen 1, and the horizontal line the nitrogen 2 per please.
Just a second.
Claudia, I'm finishing okay. 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 This, I think that is you are. This is minus, but it's not important. Okay. This is the same. You multiply the intensity of this line by the intensity of this line, of course, and this multiplication, I don't know, is dependent on the metallicity.
Okay, so this one maybe with the difference here. This is the one you're talking about.
Okay. This okay. This is good because this is the same. You are consider the intensity of the nitrogen 2 per intensity over intensity of sulfur 2. This line ratio is depending on the metallicity, and there is a little dependence on the ionization parameter, but it's not important. But about this line in the vertical, this is dependent on which parameter? I cannot see.
Okay, let me just show you another slide here. Okay, this one, which is the one with the models. So for me, this is the most confusing slide, the most confusing alternative diagnostic diagram, because in the end, when we do this subtraction, here if we do the sum and the subtraction, we are using H alpha and H beta, so it's okay. But here we will have in the end like an H alpha squared, which is a bit weird. And so we see that here we have a little overlap of the different metallicities that we do not see in the other diagrams, where the star forming sequence, which is mainly dependent on the metallicity, is better described. And we see here also that the metallicity, it has two very well-defined patterns. So all the objects with solar metallicity here and twice solar metallicity here.
Okay.
So I think that it is somehow sensitive to the metallicity, but it's when you do the difference, you sometimes you miss the information of which is hard in this comparison, if it is the nitrogen 2 or the sulfur 2. So it has a sensitivity, but it gets mixed in ranges that in the end are not very useful for us.
Okay. So when you are writing the paper, take care to explain each line relation about that, because certainly the referee will ask for you that. Take care. Okay.
Just one thing, if I am going to make a paper, I'm not putting this diagnostic diagram in the paper because it doesn't help me much. We have this transition region, so we can better constrain that here these objects are probably star forming, here these objects are probably AGN, but the AGNs are all messed up and the models are very confusing. So this is not one of the diagrams I want to make an advertisement about.
Okay. There are a paper published 20 years ago, Charlot, I don't know, where they suggest using all the optical emission lines to derive in the metallicity. You cited this paper in the text, but maybe it's good to read it with attention in order to looking for the sum of logarithm of linear relation. For me, it's new, but it's not wrong. It's new. It's good. Okay.
Thanks.
Okay. Let's see. Okay. Just a question in the page 155. You reported that the Geneva, I don't know, the Geneva evolutionary oxygen abundance values is minus 3.3. How did you get this value? Is in the paper of the Geneva? This is very important because my work is with Angela. We using the metallicity in the gas. This is in CLOUDY. It is very clear the values of the oxygen abundance, the nitrogen abundance. Okay, but if you use stellar synthesis, the oxygen and the nitrogen abundance is a mystery. Okay, you sent an email to the Brusual, the father of the seeds. Oh, Brusual, please, you compare the stellar. You have compared in a paper the oxygen abundance in the gas phase, in you need the abundance of your models, and we understand he don't know, okay, because if you move on to stellar studies, the metallicity is determined by the iron, okay, and he gave me us a answer where we don't understand which is the oxygen values used in the stellar track or model of Brusual. And now in your in your text, I have seen you got the values of the oxygen abundance in the Genova. But okay, how did you get this value?
Yes, I have to check which are the references that I use, because I did not go in the papers, the original papers of the Geneva tracks. But I think that this issue is already pointed out in CLOUDY's annual review of
Okay.
2019. I guess it is. I mean, I know that this issue is pointed out there. I'm just not sure if the value is there, but it can also be in the D'Agostino et al. 2019, which is one of CLOUDY partners in work, where he does this comparison of the several different star forming methods. So I used it despite of being aware of this discrepancy, and I talked more recently to Klaus Latherer, who is the person who did Starburst99, and he told me that Lucimara, that were also in Dalfide and that works at Cruzeiro do Sul now, she is working with the new models of Geneva tracks that will have more values of metallicity and so on. So maybe we could ask her which are the values that she is using, also because these models, they will include rotation. So I think that they will be even more useful for having a harder spectra.
Okay. You see, it's a not easy task to get this value. Okay, thank you. Okay, I'm finishing. In the page 158, you cite some relations about the carbon, nitrogen, and the oxygen. Okay, proposed by Dopita et al. Could you explain how this relation was obtained? For example, Dopita et al. 200 proposed this relation between the carbon and the oxygen and the helium oxygen.
Yes, these ones by Dopita, as far as I remember, he obtained it from a work by Izotov et al. But I read Dopita's work and I didn't read this Izotov et al. Paper. So when Dopita uses it, I see there are some works, because I went to check on these works that he took the reference from, but sometimes the equation is not explicit, and it only appears explicitly when Dopita is describing these equations to use them in the models. So that's why I use the reference of Dopita, because that's where I took really literally the expression. But he was not the one that derived the expression. He was the one that put them all together to build the models.
Yeah. Although it's a very simple question. Dopita et al. Simple compile the values of the carbon and the oxygen values of H2 regions derived by the T method or direct temperature determination, and they do a plot and they fit a curve. It's simple, like the helium. It's very simple, so it's good you put that in the paper, because it's a mystery. They found this relation, but it's not explained the source of this relation. Just that.
Thank you.
If you have more than 200 pages, one phrase does not do the difference. I'm finished. Just okay. In the description of the input of the the photoionization models, you use or there is a eating temperature of in the input. Okay, when I read that, I got confused because how Catarina put the temperature of the gas as input. Okay, it's a confusing for the later, but it's not the temperature of the gas. You are speak about the temperature of the SED because the SED consider many black modes. It's a multi-component SEDs. So in the way it's described in the text, at the first moment I thought you put the temperature of the gas as input. Okay, so just to describe better that it is not the temperature of the gas because this does not make sense. Okay,
Indeed.
This is the SED. The SED is a multi-component SED where for this wavelength range consider this alpha parameter and this component is a black mode with this temperature. I think it's this temperature we are talking about.
Yes, indeed.
Okay.
It's not an explicit input, so
Yes,
I think
perfect.
it might be clear to put inside another one.
Perfect,
yes, you're
perfect,
right.
Perfect. Okay. And I have more 2 comments. Just comment. I have H2 region photoionization model results are presented in a very beautiful grids. Okay, but the AGN models are presented in 2 or 3 points. It's okay, but why you don't build a grid like the H2 regions?
Because the grids were not beautiful as the ones from the H2 region. They were overlapping and it was a mess. So that's why we decided to just choose a few points and leave it there.
Okay, it's a good answer. Okay, the last question is this new relation for the nitrogen versus oxygen. It's a good you compare with new abundance determination with the chaos project, for example. If you look at the Daniela Berg et al., I think this last paper, there are many nitrogen and the oxygen abundance determination using the T method. It's good that you compare that. Okay.
Yes, in the ChemaGas event, there was that student, I forgot his name now, Connor, I forgot it, but he was from Cambridge and he made a presentation and he was with a paper to just come by. So I'm also waiting for this paper because we have changed some ideas and he knows a little bit more, because my main issue with this expression is that I don't know what theoretical basis would explain it. And it's just a better fit between the models and the data. But the models themselves are not that robust. So I'm not very confident about it, but I have shown it to him and he was interested. So yes, maybe talk to these people that I have met recently. It would be great.
Okay. So Catarina, just as a last comment, I think you have separated the analysis in 2 parts, in my opinion. Claudia, feel free, don't accept my suggestion because it's a little confusing. or in two chapters. Diagnostic diagram in a chapter and the photoionization models in another one, because it, for me, got a little confused. Okay. And you have to believe in your work to publish that. Okay. Believe in yourself, because sometimes it's difficult, because diagnostic diagram are studied by several people, but it's not a problem. Believe in yourself, and you get publication. And it's my opinion. You separate the publication in two. First, the diagnostic diagram, okay, and after the photoionization models. Because if you put together both, it's confusing for me. Okay, thank you very much. Congratulations.
Thank you, Eli.
I know Catarina is beyond of the knowledge, the conhecimento of a master students. Okay, congratulations. I'm happy to participate of your defensive. Okay, thank you, Claudia.
Thank you, Oli.
Oli, thank you very much for your participation and also for following Catarina.
Okay.
We're just discussing things with Jean as well. We know your participation.
Okay.
Roderick, would you like to say something now or after Maciel? Okay. We go now to the third person, the third evaluator, Dr. Walter Junqueira Maciel, and I would like to thank Maciel for following the student closely, since he's the one that looks at all the reports of the students regularly. So please, the floor is yours. Thanks.
Thank you, Claudia. First, I would like to congratulate Catarina for finishing this work. This 1.5 years has been particularly difficult for everybody because of the pandemic. And Catarina had an additional problem with the loss of her advisor. And the fact that she has finished the job within a reasonable time, it was something very difficult to do. As Claudia mentioned, I have been doing the reports for the department for the last 2.5 years. So I have had many opportunities to read the work during its progress, and which included some oral presentations by Catarina. So I have had the opportunity to discuss this with her several times. But still, this is still the first time that I could read the project from beginning to end. So that was very interesting. About the thesis itself, it was, I would say, it's very well written, especially that it was written in English, very few mistakes. The references are quite up to date. But again, I agree with Oli. It's a very long thesis, a very large thesis, and especially because there are too many repetitions. And I think it could be the thesis would profit for being more streamlined. I think that is something that could have been done. I have a very long list of comments and corrections, actually more comments than corrections. I will send you, Catarina, after the thesis. And I will send also a PDF of your own thesis with my own comments, so you can compare both things and do the changes that you think are important to do. I don't expect you to comply with all my comments, but at least some of them, or especially corrections, I think should be done. I have one general question. I think this is looks to me more than enough for a master's dissertation. Have you considered doing changing this into a PhD thesis?
Okay, so first I'm going to just make a comment for why this thesis is so long. It's not just because I am a little bit not very concise with my answers, but also because the structure of the thesis was already set with João. And so I decided to maintain it. And Roderick really helped me by cutting these things. And he already pointed out it was even more repetitive before I sent it to you. But I had difficulty on not putting things that I told him that I would put. So maybe that's why it's a bit too long. And I remember you telling me in the first report that we did orally about it, that it was a little too big for a master thesis. But in the end now, since I want to focus on higher redshifts for a PhD and another kind of object in the end, then I think I would just leave this behind, trying to maybe publish a first author paper and then go to the next steps.
Okay. I forgot to say that I would like to congratulate Claudia and Roderick too, because they have taken up this job in progress. And I have done that myself in the past, and I know it's not very easy. Another question, which is a general question, you say, Catarina, in several parts of the dissertation that your proposed alternative diagrams, they use the same data as the traditional diagrams, so that they have the same impact in practice, they have the same limitations. So as a general question, I would say, I would ask you, do you think it's worth to take the trouble of doing all these alternative diagrams, or it's best to keep using the traditional diagrams? What's your opinion?
Okay, let me just share my screen to give the example. So the limitations indeed are the same, meaning that we are not able to discern shocks and diffuse ionized gas and old stellar populations. But in the end, I do believe that there is an advantage, mainly in the use of this diagram, which is the one I think that gives the best results for us, because we do not have this issue of having a single object that can be classified differently if we have only one diagram that gathers all the information that we need. So this diagram, it has kind of a similar shape. It's also based on mainly on the hardness of the field, but it's also sensitive to the metallicity in the x-axis and to the ionization parameter in the y-axis. So I do think that using this can simplify us from using the three diagrams separately.
Okay, sorry, I even got my headphone, but I forgot to use them. Okay, I will turn it off. Okay, based on what you just said, are you planning to write papers on this? Because if I remember correctly, you don't say anything in the thesis, but you just mentioned something to Oli right now. So are you planning to write an article or more articles on this?
Yeah, in the moment it's a bit confusing because we are waiting for FAPESP's results for a PhD. So if it gets accepted, then maybe I have to focus on this next steps. But if it does not get accepted, then I have some time to make this paper. So it's not very clear, and that's why we do not indicate it in the thesis, because we are not sure if I'm going to make it on time, but it's an idea.
Well, I'm not sure I agree with that, because, I mean, irrespective of your PhD project being accepted or not, I think you should work hard on the papers, because you'll be asked about that later on. And in my experience, the longer you take to write the papers, the more difficult they will become to write. So it's important to have in your CV these papers, or one paper at least. So since it's a master's degree, I mean, you cannot ask too much. So I would like to suggest you to serious consideration this possibility. Well, as I said, I have a very long list of comments, and I cannot make all of them here, or even a small part of it, since I guess I don't have as much time as I would like to, if you want to keep this presentation within a reasonable amount of time. But there are a couple of things that I would like to comment. For instance, you mentioned the ionization parameter lots of times, and you only define it in the end of the thesis. I think since you are using it so many times, I think you should have defined it in the first time that you mention it. It's on page 33. So I would suggest you to move the definition from where they are now, it is now, to page 33, or even reproduce both of them. It doesn't matter. Another thing that, for instance, on page 37, you mentioned the heating of it to regions, and you only mention about the photoionization rating, but you don't mention the photoelectric heating by grains, which is very important in this kind of object. To be true, you mentioned it on page 155, but not on page 37, as where it should be mentioned for the first time. What else? Well, there's something here, but you have to read it because I don't have time to discuss this right now.
Yeah, thank you. I'm pretty sure that it will also help me not only to make the thesis more properly, but maybe to write the paper more easily when it comes.
Okay. One thing that struck me, it's the following. Whenever you write a thesis or a dissertation, usually it's very important to distinguish between the things that you have done and the things that you have read in other papers, and that difference is not very clear in your work. For instance, even in your first chapter in the introduction, you use results, if I understand it correctly, you use results that you got yourself from Sloan, applied to the different papers that you mentioned, Nuclei and the others. But you don't show your results very clearly. You just mention that you have applied that to these papers and got some results that are somewhat different in between compared with these original papers. I think it would be important to put that in the thesis. That is something that I think it was missing from your work. Yeah, I know you did it because you mentioned that you did it, but you don't show it. So I think that would be important to distinguish between what you read and what you have done. Can you comment on that?
Yes, maybe I could put that on the appendix, this comparisons, but indeed, since it was already kind of a very long test, and there are some things that when they were not fruitful, let's say when they did not give good results, for example, tasks that show that it was not the right path, then I just mentioned that we did tasks, but it did not work. But yes, giving the examples would be good. And also these comparisons, for example, the economic diagnostic diagram, it has been proposed several times, but none of them had used the high quality data in order to see the hook shape that the star forming sequence shows. But I only mention it, I do not show that this comparison of other works, so indeed.
That's exactly what I mentioned, because if I understand it correctly, you are the only one who has used these modern Sloan data to the older works, and that's the original. That's interesting. Something more, let's say. About the redshift separation, you have used a limited range of redshift. You said that I understand that the data you have used is have lower uncertainties, if that's what I understand, which seems okay. But somewhere in it is, I think it was on page 103. You seem to say that there is not much difference between low and high redshift. Is that true?
Let me show here once again, just a second. Okay, so this is the diagram where I show the effects of, of the aperture effect. So we see that in this, well, we are considering both a redshift range and signal to noise, let's say, like of the emission line, so an error bar range. And we see that for higher redshifts, we have indeed a higher concentration of objects in all the classification types, or all the classes. But we made this plot here to check if there was a trend on having more transition objects according to the redshift, because that could indicate that there will be more starlight contamination from the outskirts of the nuclei to the real nuclear region. But since we see that, yes, we do have more transition objects, but we do have more of all of the classes, then we do not find that to be a significant trend in this redshift range. But other works that have considered higher redshift ranges have found such relation. I'm not sure if this was the example you were asking about, but this is the, let me show here for you to see the redshift comparison that we considered.
Yeah, okay. I just got the impression, because you mentioned that the results don't seem to be very different. Later on page 114, you mentioned that the range between H alpha and H beta is small. You consider it as constant, but if I check it in the figure, it's between 2 and 10. The range between H alpha to H beta. That seems to be very large to me. You don't think so?
Yes. For most of our objects in our sample, it is in the expected range between 2 and 4. But indeed, we have some of these objects that reach to very high values, and I agree with also what Oli told me to check on the reddening correction to see if it was properly applied. But indeed.
Okay. When we consider the changes, the physical properties within the ionized gas, if I remember it correctly, you don't mention temperature fluctuations, which is something that is being considered by people working on the H2 regions, apart from density condensations or other kind of physical processes. Have you considered or at least mentioned the fluctuations, especially work by Pembert and other people?
Yeah, I think that I focus mainly on the density because that is the parameter that we can set in the models. But indeed, we have this temperature fluctuations, and we also see some ionization fluctuations, and all of these will affect on making the nebula more complex to model and describe.
Well, okay. I have several other comments, but I'll leave them for the written comment that I'll send you. So again, congratulations to you and your current advisors, and very nice work. Thank you.
Thank you very much, Professor.
Okay, thank you very much, Walter. I would like to say a few words. I was going to say at the end, but I think that now it's a good moment since several of you have already mentioned. I'd like to say that the situation, the special situation under which this work was done, Catarina was a student of our friend and colleague João Steiner, who passed away in September. And, you know, João was very deeply involved in the work, very active, since he was really a dedicated advisor. And many of the plans that Catarina had came from that, and some had to be aborted. And at that time, she had already 3/4 of the thesis or the work done. And I came into the scene as the official advisor of Catarina, and also the responsible person at in front of the FAPESP fellowship. This was important as well. But however, I want to thank a very important person in this process, which was Roderick. And I acknowledge that he was the person who actually rolled up his sleeves, and then he helped the student in every step, and was really the person who was there day to day to push the research forward. And this was really important in this moment. So I'll really, independent of the result we get here today in this evaluation, I first would like to congratulate Catarina for getting to this point, because it was really hard and she overcame all the difficulties. And I was really proud of her that she was able to do this today without getting emotional, because so much of this is involved in this history of João Steiner. And but I also would like to deeply thank Rodrigo Bezier for not hesitating to join forces and to make the completion of this dissertation possible. Without him, this would not be possible. So having said that, I'd like to just ask Rodrigo if he wants to say anything now.
Can I say what I want to say after we announce the result?
Oh, yes, for sure.
Thank you, Barbara.
I think we just break here, then we go to another room where we're going to have the evaluation, and then we come back to give the result. Okay, Catarina?
Claudia,
Yes.
would I speak in some few words? I see this FAPESP procedure of evaluation taking account the number of papers, okay? But Catarina, in my opinion, she knows many things more than a common student. At least she does not have a paper. We submitted a paper where she is co-author of my master's students, and probably we will have a paper, I hope in 2 months. But this is the problem of the FAPESP IT, or then taking account the number of papers in sometimes this is not correct, because I participate of the committee of some students, and he or she did not the physical process in gas nebula, and you have seen now that Catarina know more than she presented now. So she is in a high level of master students.
Thank
okay?
you. Thank you very much.
This is my opinion, and I hope FAPESP take this in account and does not do a account. She don't have paper, she have a submit paper. For that, we will not give the scholarship. For me, this is wrong. Okay, they have to take account the student, because she is not just a number. She know more than the common students, because I know there are groups and the students finish the master thesis with 5, 6 papers, but they don't know anything about the papers. And if you do a ranking, of course, they will are in the top list. And Catarina is not the first, but she knows a lot. In my opinion,
we
yes,
will ask you to write a reference letter for her for FAPESP.
yes, but
we need to break for the evaluation, and then
okay,
we can continue with that. Thank you very much. Okay, so let's break. Richard, I don't know what we have to do here now. Can you direct us? Okay, thank you. Yes, we have to say participate.
Okay, I will be right back. My interphone was ringing a lot, so let me see what happened. Okay. Thank you.
Go ahead, Catarina, pick it up. Go ahead, pick it up.
Roderick, did you send the iPhone now? Okay, I have to pick it up in the elevator and I'll be right back. Thank you. O Roderick saiu da reunião para não poder agradecer, poxa vida. Estou... Indo para lá, entendi. Eu sou muito mimada, gente. Eu ganhei o Xandão e um monte de docinhos de padaria super fofos, sério. Ui. Bom, nesse momento de espera, primeiro um alô para todo mundo que está no YouTube, bem blogueira. Muito obrigada por todo o apoio, eu amo muito vocês. E para passar o momento de tensão, que já passou um pouquinho, porque eu ganhei um monte de presente, eu vou ler o poema que está na minha dissertação. Livrinho aqui do Pessoa, no caso, é um poema do Alberto Caeiro. Deixa eu tomar uma aguinha antes. Ui, que nervoso. Respira fundo. O mistério das coisas, onde está ele? Onde está ele que não aparece, pelo menos a mostrar-nos que é mistério? Que sabe o rio disso, e que sabe a árvore? E eu, que não sou nada mais do que eles, que sei disso? Sempre que olho para as coisas e penso no que os homens pensam delas, rio como um regato que soa fresco numa pedra. Porque o único sentido oculto das coisas é elas não terem sentido oculto nenhum. É mais estranho do que todas as estranhezas, e do que os sonhos de todos os poetas e os pensamentos de todos os filósofos. Que as coisas sejam realmente o que parecem ser, e não haja nada que compreender. Sim, eis o que os meus sentidos aprenderam sozinhos. As coisas não têm significação, têm existência. As coisas são o único sentido oculto das coisas. Alberto Caeiro, e esse eu dedico para o meu vozinho, meu vô Roque. Acho que ele não está assistindo agora, mas acho que ele mandou good vibes mesmo assim, na medida do possível. E queria agradecer muito todo mundo que me deu força, e principalmente nesses últimos dias. Quem não sabe, eu talvez esteja com Covid, talvez não. Primeiro teste deu negativo, veremos o teste de amanhã. E por isso que a dissertação aqui saiu pior do que as prévias, é claro, porque no começo eu estava toda entupida, indo devagarinho, e aí no final, meu Deus, eu tenho 10 minutos para falar, tipo, 1/3 da apresentação. Então, ficou um pouco corrido, mas faz parte. Se vocês tiverem dúvidas e perguntas, depois vocês me mandam. E eu vou ler depois, todo mundo que deu um alô aí no YouTube, e vou mandar mensagem, vou agradecer pessoalmente. E quem não deu um alô no YouTube e não me mandar mensagem, eu não tenho como saber que você me assistiu. Então, me dê um alô depois. Eu, provavelmente, logo depois da dissertação, eu vou só morrer na cama por algumas horas. Mas depois a gente se fala e eu respondo as mensagens que forem. E é isso, hora da verdade. Richard, você acha que dá tempo de eu ir no banheiro? Ou você acha que eles... Meio não tem como saber, né? Então, voltando. Não, beleza. Obrigada. Thank you for the gifts, Roderick. That's very kind of you.
It's on behalf of all of us. But let's not open until we have announced the result.
Oh, no, I'm not going to open today, unfortunately, because of how I am. But when I celebrate it, then I'll let you know.
I can't hear. Mute.
I was giving the good result and you didn't hear anything. Come on. So the committee has got together and has discussed the content of the individual evaluations that we had here today. And we consider the work is very good and the student is approved and she can hold the master's degree from the University of São Paulo.
Thank you.
Okay.
Thank you very much.
Congratulations.
Congratulations, Catarina. This was a fantastic job. We all recognize that.
Thank you. Thank you very much. Yes?
Congratulations, and also, of course, to recognize Roderick's and Claudia's contribution, of course. Congratulations.
So, Claudia, if I can have a minute?
Yes, for sure, Roderick.
Right. So, dear Catarina, it was a true pleasure working with you. I actually knew your name a long time before we met, and that's because João frequently talked about this wonderful first ESA student and later master student that was working with him. And, you know, João was not easily excited about things. So your reputation came ahead of you. And I think we probably first got to know you better during the first Light School, where it became very apparent that not only do you have a talent for research, but also for organizing things, right? And I should warn you that if you don't watch out, you will risk being put on every organizing committee, which I think is already happening. So there are, of course, so this is something that I think Walter and Claudia and Oli also touched upon. There are students that have perfect grades, that are masters at coding, or that have written papers. But you should not be intimidated by this, because you possess a very rare combination of not only what we call the hard academic skills, but also what we call soft skills. No, these are actually the skills that are extremely hard to teach to anyone. And these are things that relate to knowing how to read papers, knowing to ask the right questions, not being afraid to ask questions, not being afraid to talk to anyone, no matter what is their academic status, knowing how to give presentations well in at least 2 languages. And in my experience, having taught a number of students, these are actually the skills that are the most indicative of success, whether you continue in academia or whatever else. So, of course, you were presented with hardship during your project in a way that no student should ever have to face. And I'm not even talking about the pandemic. And we really admire the way that you managed to carry yourself in a way that you almost had to become your own supervisor really fast. This is probably not allowed officially, but I think you should print out your thesis and write your own name in the list of advisors of your thesis. So both me and Claudia would like to congratulate you with all these accomplishments. Anyone will be very lucky to have you in their group or their team. You're very welcome to stay at IAG, but we mostly want to encourage you to find whatever step is the best step for you. And we don't doubt that you will succeed in whatever it is that you end up doing. So congratulations again. We have already sent you some materials for celebration, but we hope that this pandemic ends soon, because these virtual parties, they are getting really sad. No? So congratulations.
Yes, Catarina.
Thank you very much. And yes, I would like to thank you all. You were very important in these last steps. And this is the moment where I'm making a dream come true that I put in my head when I was 16 years old, and I have my first astronomy classes, and I said, oh, I want to be somehow an expert about it. And everyone that met me along these 9 years have seen that it was not easy, but still, I never wanted to give up. So that's why I always seek for help, and I had a lot of help, and I'm very, very grateful for that. Thank you very much, Claudia, Roderick, Oli, and Walter as well. You helped me a lot, and Montse also now. It was a pleasure to meet you in these final steps. And I also really thank my family and my friends and all the support I have, because I know that that's where I get the strength to move on. So thank you very much for everything.
Thank you.
And thank you, Richard, that is here with us, always helping us as well.
Okay, so thanks a lot, everybody, again. And thanks, Catarina, and congratulations for the milestone. And I hope you'll be here for your PhD.
Yes.
Or not, or maybe you're going to do it abroad, which would be great also. Yeah, look forward to that too.
But you do it wherever.
Yeah.
Okay, Richard, can you guide us here? Do you have to do anything else?
Just a little in Portuguese then. Muito obrigada a todo mundo que está aí assistindo, que me deu apoio esses anos todos. Eu amo muito vocês sabem disso. E daqui a pouco a gente se fala off. Obrigada por tudo.
Okay, thanks a lot, everybody. Ciao.
Ciao.
Bye-bye.
Bye bye. Thank you.